Welcome back to our statistical journey. So far, we've explored fundamental concepts like hypothesis testing, means, and standard deviations, and even delved into comparing two groups using t-tests. But what happens when your research question involves more than just two groups? What if you're comparing the effectiveness of 3 different teaching methods, or the growth rates under 4 distinct fertilizer types? This is where our previous tools fall short. Imagine trying to compare the average scores of students from 3 different schools using only t-tests. You'd have to perform multiple pairwise comparisons, School A versus B, School A versus C, and School B versus C. While possible, this approach dramatically increases your chance of making a type 1 error, falsely rejecting a true null hypothesis. Each test has a small risk, and performing many tests compounds that risk. This challenge leads us to a more powerful technique called ANOVA, which stands for Analysis of Variance. Despite its name, ANOVA's primary goal isn't just about variance itself, but rather about using variance to compare the means of 3 or more groups simultaneously. It's a cornerstone in statistical analysis for understanding differences across multiple populations. At its core, ANOVA works by partitioning the total variability observed in your data into different components. Specifically, it looks at 2 main types of variance: the variance the groups, which is attributed to the different treatments or conditions, and the variance the groups, which represents the random error or individual differences not accounted for by the group membership. The magic of ANOVA lies in comparing these 2 variances. If the variance between groups is significantly larger than the variance within groups, it suggests that the group means are indeed different from each other. This comparison is quantified by what's known as the F-statistic. A larger F-statistic indicates greater differences between group means relative to the variability within groups. While we're focusing on the general concept, it's worth noting there are different types of ANOVA. The simplest is one-way ANOVA, used when you have one categorical independent variable and one continuous dependent variable. More complex designs, like two-way ANOVA, allow you to examine the effects of 2 independent variables and their interaction. However, like many parametric tests, ANOVA comes with certain assumptions that your data should ideally meet for the results to be reliable. These include the independence of observations, the normality of the dependent variable within each group, and homogeneity of variances, meaning the variances across the groups should be roughly equal. So, what happens if your data doesn't quite fit these assumptions? What if your data is severely skewed, or you have extreme outliers, or your sample sizes are very small, making it difficult to assume normality? This is a crucial question, as real-world data often deviates from these ideal conditions. When the assumptions of parametric tests like ANOVA are violated, or if your data is ordinal or nominal rather than continuous, we turn to a different class of statistical tools, non-parametric tests. These tests are incredibly valuable because they don't rely on strict distributional assumptions about the population your data comes from. Non-parametric tests are often referred to as distribution-free tests. Instead of working with means and standard deviations directly, they often analyze ranks or signs of the data. This makes them much more robust to outliers and skewed distributions, providing a reliable alternative when parametric tests are not appropriate. To give you a glimpse, for comparing 2 independent groups without assuming normality, you might use the Mann-Whitney U-test instead of an independent samples t-test. When comparing more than 2 independent groups in a non-parametric setting, the Kruskal-Wallis H-test steps in as the non-parametric equivalent of a one-way ANOVA. There's also the Wilcoxon sign rank test for paired data. The power of non-parametric tests lies in their flexibility and robustness. They are particularly useful when dealing with smaller sample sizes or data that is inherently non-normal, such as ratings, satisfaction scores, or other ordinal scales. While they might be less powerful than their parametric counterparts when assumptions met, they offer a trustworthy solution when those assumptions are not. Deciding whether to use a parametric or non-parametric test is a critical step in your analysis. It largely depends on the nature of your data, especially its distribution, scale of measurement, and whether it satisfies the underlying assumptions of parametric methods. Always consider these factors carefully before choosing your statistical approach. This introduction to ANOVA and non-parametric tests merely scratches the surface. These are powerful tools that open up a new realm of possibilities for your data analysis, allowing you to tackle more complex research questions. We encourage you to delve deeper into these topics, exploring their nuances and practical applications, as they are indispensable for any serious data analyst or researcher.